to Salt Lake City. Thank you for those who have jumped online this morning. We have over 50 people registered, so I think we'll be seeing a lot of people jump into the room as we get going. My name's Alistair Reid. I'm at HydroTerra in Melbourne, and I'm joined by Jared Ewers, who's also at HydroTerra.
Hello, how you going?
And we have Ryan Blanchard from Willowstick over in Salt Lake City. Can you say hello, Ryan?
Yes, happy to join. Hello.
Fantastic, and you're coming through loud and clear too, which is fantastic. So I'm just I'm the MC for this morning. And the way it's going to work is we're going to have an introduction and an overview of Willowstick, and that's going to be presented by Jared. And then we're going to move into a case study presented by Ryan, which is going to be extremely interesting and showing Willowstick in full application from go to woe. As part of that, we have a few videos which have been working very nicely. And at the end of that, we'll have a question and answer session in the remaining time. And to conduct that, if it all goes to plan, there should be a little raise your hand, ask a question button. And if you click on that, you'll enter a question queue. And we'll get to as many questions as we can. But any questions that we can't get to, feel free to get in contact with us after this webinar at any point, and we can go through any questions that you might have. So without further ado, I'd like to introduce Jared Ewers from HydroTerra to give us the overview of Willowstick.
No worries. Well, thank you very much, Alistair. Welcome everybody to our webinar today. We're very excited to be working with Willowstick, promoting their technology. I guess if you can see the slides there, first slide there. So Willowstick is a technology company based in Salt Lake City. Willowstick technology is basically it's an active, non-intrusive geophysical application. It's used to identify, map, and model preferential groundwater flow paths and patterns. So, we've completed over 275 projects worldwide. It's been over 12 years of developing this patented technology. Yes, the method uses a signature electric current to image and visualize water through the subsurface, able to produce either 2D maps and 3D models, and to, I guess, model the distribution of groundwater. We'll speak more about that later, but I guess to looking at the background a bit more, technology is transforming industries around the world, and I guess both HydroTerra and Willowstick, we see the importance of using technologies to promote the importance of data. Big data sets, we want to collect more data. More accurate data will help us make more informed decisions. I guess looking at this technology, originally when Willowstick began, the technology, the instrument that it uses, will take a reading every 15 minutes, but technology now is advanced, so this instrument's able to take a reading every 8 seconds. So this is an example of where technology is taking us today. Moving on to our next slide there. This technology is being used all around the world. As you can see, there's a presence across North America, South America, through Africa, Europe, Asia, and Australia. I guess we understanding the importance of managing water assets as water is becoming more valuable. Therefore, we've got to look at the pace of adopting technologies, and this technology is truly being utilised across the world. As some of the more wealthy countries become dry, there's an increased need to see what is going on beneath the surface. So, where is this technology being used? Yes, there's a few areas of focus here. Those top 4 there are where the technology has historically been focused on. But more recently, Willowstick is using this kind of technology to, I guess, identify and leaks in water, wastewater pipelines, more recently in tunnels as well. So, for example, in Victoria, we're looking at a major project at the moment with a metro tunnel. So this technology potentially could be something that could be used to identify potential leaks in a tunnel. So what are Willowstick's sweet spots? I guess we've spoken about using this technology to identify leaks or seeps in dams. We can map subsurface flow paths, trying to identify where contaminated groundwater is moving below the surface. This technology is quite powerful. We'll look at it a bit more later, but it can, I guess, identify and characterise groundwater up to depths of 300 metres. That's part of this patented technology we'll talk about. Also able to identify and characterise leaks in pipelines, as we've mentioned. So more about the technology. So this technology uses basic principles of physics. As you might have learnt in high school and university, earthen materials are poor electrical conductors. However, water is a good conductor of electricity. And when water is present in these subsurface materials, it increases the conductivity of earthen materials. As we know, both water and electricity follow the path of least resistance. Water flows from areas of high potential to low potential. Part of this technology, well, as we know, electric currents generate magnetic fields, and this is what the Willowstick technology does. It measures the magnetic fields that are produced. So the technology basically works by establishing a signature electric current within the groundwater of interest, and the distribution and flow of this subsurface electric current is then revealed by measuring the signature magnetic field. So often a specific signature frequency of 380 Hz is used, and this is done to avoid the harmonics of power frequencies in common use around the world. While operating a low frequency, it allows the characterisation of groundwater up to 300 metres or 1,000 feet. So the data is then processed, 2D, 3D models, which we'll look at later in some of the case studies presented by Willowstick. It's quite powerful, and these models are then interpreted. This all sounds great in theory, but what does this look like in the field? So this next slide, we're looking at here, the typical survey configuration, helps us understand what this the setup would look like in a typical investigation. So remembering this technology, it's a magnetic technology. When we set it up in the field, we normally need to place an electrode upstream in a high potential area in a water-bearing zone. So you can see on this slide here, we've got an upstream electrode on the left and then a downstream electrode. So it's important that these electrodes are placed in water-bearing zones. This might be a dam or a reservoir. In some cases, a groundwater well can be used or a bore. And then, I guess, wires are laid out that are connected to the electrodes. And these circuit wires are laid out away from the study area. Now, it's important that when the setup of this whole study and survey, it's important that the wire is laid out in a large area away from the study area, because the electric current from the wire will become the dominant signal. And we want to identify the signal in the underground water-bearing zone, not from the wire that's laid out in the study area, away from the study area. So sometimes the second electrode may not be able to be placed in a water-bearing zone, but so I guess the electrode could be placed into the earth, but sometimes it's important that we soak this area with water. It's vital that we complete the circuit, because this technology is based on generating a magnetic field. We want to be able to measure this to accurately pick up what is happening in groundwater flow beneath the surface. So I guess by placing these electrodes in specific areas, I guess we want to energize the study area from multiple perspectives. We've said we can use wells, seeps, reservoirs, and I guess by doing this and energizing this area, we can have a high degree of confidence in picking up potential groundwater flow paths. Looking at the instrument itself, I guess the technology, the patented technology, lies in the magnetic coils there. You can see on this instrument, it's an instrument that is quite easily carried out in the field. It looks like some sort of survey stick. It's very, very clever technology. The magnetic coils are the size of the D batteries. They weigh about 6 kilos. And the power of these magnetic coils are such that they can pick up, well, they can read up to 300 meters below the surface. If you were to find magnetic coils as powerful as this anywhere else, you'd be looking at something the size of semi-trailers to support the weight of them. You can see here it's quite a good setup with a GPS antenna, portable computer, data logger, and this instrument can be used to take a reading every 8 seconds along a grid pattern. Moving on to our next slide there. So, what are the key differentiators of Willowstick's technology? As we've said, it's a non-intrusive geophysical technique. It's unique in the marketplace. It's a patented technology, and it's been created specifically to characterize flow paths. It's able to define the edges of groundwater. It's able to identify primary zones of flow and pick up edges of flow paths. I guess some of the additional benefits of using this technology, if it's combined with selected drill holes, it's able to explore quickly large areas at a much lower cost than traditional approaches. A lot of costs can be utilised in installing many wells, I guess, trying to identify flow paths or leaks in dams, etc. And this type of technology is able to characterise large areas quite quickly and produce models that can help with decision making on how to remediate, whether it be utilising cut-off walls or grout curtains. So looking at field work, as we've said, this technology, it's a much quicker way of identifying groundwater flow paths. The surveys themselves can be completed in a few days. The technology is advanced now to be able to take a large amount of data over a few days, and it's a real-time surveys will adapt to suit most environments. There are some, I guess, restrictions in laying out the wire sometimes, but they're able to be able to adapt to most sites. So does this technology really work? Well, Willowstick have completed over 275 projects across the world. It uses simple physics, well understood scientific principles. The models it generates assist greatly in mapping groundwater, targets groundwater at specific depths. The technology signature magnetic field is not attenuated or altered by conductive overburden. Yes, MRI, magnetic resonance imaging, has changed medicine, so it can be used in our field too. I guess with any technologies, there are potential limitations. So this technology works based on measuring contrasts. There's no contrast, and it's not going to be utilised very well. I guess conductive culture, such as metal objects, do need to be identified, and this can be done prior to field work. We need to understand where man-made culture sits, things like metal fences, railroad tracks, metal pipelines, power lines, cables, conductive culture, and potentially steal the signature electric current. The models, though, can filter out, have filtering algorithms that can filter this out. We want to identify groundwater, what it needs to be conductive to highlight these flow paths. So I guess the Willowstick strengths the school train operators to collect this data, and then also the technologies in terms of filtering out conductive culture is part of this whole modelling process. Well, thank you. We'll hand it over to Willowstick now for some of the case studies.
Yeah, thank you, Jared. And yeah, over to you, Ryan.
Okay, well, thank you. So for the last part of the webinar, I wanted to take a few minutes to show you how the technology works. I prepared 2 case studies from recent mining projects that we've performed a Willowstick investigation. I was asked to focus on mining, but as Jared mentioned, we have done Willowstick investigation in a number of applications. And so for the purposes of today, I'm going to show you 2 mining projects. So the first one is a project we conducted a survey on a zinc mine in North America. And I hope this will help illustrate the power of our technology. To provide you with a little context and to orient you, you can see here this is the waste rock dump. There's also a drainage collection trench all along here. And then there's a tailings storage facility here. The client had tested the tailings storage facility and had seen that acid rock drainage was bypassing the drainage collection trench, and it was making its way into the tailings facility. And so Willowstick was tasked to confirm some of the theories of the client, but more importantly, to provide a better understanding of exactly what the flow paths this acid rock drainage was taking. And so to give you an idea, this is an illustration. I had a number of monitoring wells installed throughout the site to understand what was happening. And so our data that we provided to them really helped give them more color and clarity to what they were seeing in these monitoring wells. So with the information that we received and the briefing that we got from the client, we then designed a series of 4 surveys along where the drainage collection was. And you can see here in white, these are the 4 surveys. So for the purposes of the demonstration today, and just for the sake of time, I'm going to focus on just the results for this survey number 3 you see outlined in black. But it's important to understand we did perform surveys all along that drainage trench. So just to help you orient you and give you a little context, for each project, we place we have 2 electrodes. We place the down gradient electrode, in this case in the tailings storage facility, and then we place the up gradient electrode in the waste rock dump itself, and then we connect those via a 14 gauge copper wire. And then you see these white lines here. These represent the distribution of the electric current through the area of interest. So in other words, we energize the circuit and inject an electric current through the area, We use a signature frequency of 380 hertz. Now, the reason why we do 380 hertz is so we can filter out any noise which comes from, power lines or anything else. 380 hertz is not a harmonic of 50 or 60 hertz, so we are able to detect that signature frequency. We call it our heartbeat signal. And like I mentioned before, the survey area is outlined in black, and then you see each one of these little red points represent one measurement station where we took a measurement with our instrument. So just to give you a better idea, and we already mentioned this and showed a conceptual model, this here is the Willowstick instrument. Jared mentioned it's very lightweight, and it's handheld. This here is one of our field crew chiefs. He's taking a measurement with the instrument. You can see the coils and the data collection units, and everything else is housed in these two compartments. And then, as Jared mentioned, each measurement takes about 8 seconds, and we are collecting hundreds of data points with each one of the measurements. And then each project, we usually take about 1,000 to 2,000 measurements. Okay, so I'm going to switch to a video here. So just to give you a better idea, we already mentioned, what I'm going to show you this is simply a member of our data team scrolling through one of the spreadsheets that contains all of our data. So each row is one measurement, and then each column is a data point. And the point of really showing an idea that this is truly a big data solution, and big data is kind of a buzzword in the tech industry right now, and so I'm sure you're well aware. And the reason that it's a buzzword is because we gather massive amounts of data. It allows you, if you have the right tools and algorithms, to begin to recognize patterns, and then you can make informed decisions based on those patterns. And so that's truly at the heart of what Willowstick is trying to do. Is we will gather a large amount of data, we'll recognize those patterns, we'll then provide that information to clients so that they can make informed decisions based on that. So back to the case study, the first step after we design the survey is we then calculate the expected magnetic field. And that's what you're seeing here. Basically, what that means is if there are no flow paths in the area, we take a picture of what the magnetic field would look like, and then we calculate that. And so you are aware, we are well aware that there are flow paths in the area, but this serves as a baseline from which we can compare our observed data set and identify any changes, where it's different. And so that's the first step. Then we go out into the field and we take our measurements at each of those little red stations that I showed you on the previous slide. And for this particular job, we did, like I said before, 4 surveys. It was about 2,600 measurement stations, and it took us about 2 weeks to complete the field work. And so what you're seeing here is a map of the magnetic field data that we observed by taking those measurements. And I want to call out just a few things. You will see a few of these areas here where the intensity of the magnetic field is really focusing, and it's really strong. And those are areas of where we've identified conductive culture. What I mean by that is that in this particular job, there was some still tanks and other buildings where some of the current was focused. And so we often get questions about how conductive culture affects our technology, and I wanted to show this to you specifically because it's obviously clear where the culture is, and as long as we are aware of it, either beforehand, preferably, or when we are on site, we can filter it out so that we are just seeing data from flow paths. And then the other thing I wanted to mention on this is that this map isn't meant to be interpreted directly. This is simply a map of the raw data that we can use for comparison. So where it really becomes interesting is when we were able to compare the observed data with what we expected. And this next slide is what is called a ratio response map. And that's what you're seeing here. This highlights any anomalies. And so basically all this is showing is where the areas in which the intensity of the magnetic field is greater than expected. And so there are basically two factors that we need to pay attention to in this ratio response map. The first one is color. So you see the areas here in green where the intensity of the magnetic field is much greater than expected. And then in purple, those are the areas where the intensity of the magnetic field is less than expected. And then in white is where it's about the same. So that's one factor that's really important. The other factor is the shape and the proximity of these contour lines that you're seeing. So when our data team looks at this data, those are really the two things they're looking for. There's obviously from this you can see a primary flow path through here, and then you can see some very subtle secondary flow paths right through this to give you an idea. So that's kind of the next step. Go to that. So once we've laid out the ratio response map, we can then interpret the data to find these preferential flow paths. And that's a really important step that we need to begin our 3D modeling, which is what I'm going to show you next in the video here. So once we have laid out, once we have identified the general location of those preferential flow paths, we'll basically create a 3D model. I'm going to push play on this. And this 3D model, you see, we're taking little cells of the area below the survey area, and then we begin to take slices of the data to identify the characteristics. We're identifying the exact location, the depth, and the coordinates of these flow paths. So what you're seeing here is a member of our data team. He's taking slices of the Y and the Z axis to be able to better understand these flow paths. And so you can see he's taken one slice and he finds something interesting, and then he's going to add a few other flow paths along the way. I'm going to stop this right here to show you something really interesting. It'll allow me. All right. I don't think it's going to allow me to do that, but let me push play one more time. So there are three preferential flow paths that are being identified on this, and that allows us to be able to then go do a 3D model of the site. So with that information, I'm going to show you the final thing to provide some context. So this is what you're seeing here. For our final report, we provide a prioritized table of the coordinates with their depth and elevation. And you see these flow paths are following contour lines because we received the contour map from the client. And I'll let that video play and then I'll back to the presentation. Okay, so this is a picture of the surveys again. We performed a few surveys. I just wanted to show you these three are the preferential flow paths that I already talked about, and then we identified a few other along this whole drainage collection trench. And then where it becomes really valuable, as I discussed before, is when we're able to provide in our final report a table. This table has the coordinates, it has the depth, it has the elevation, so we can prioritize them based on relative size. As you can see here, we've identified 3 primary flow paths, and then there are a few secondary flow paths as well. And this is the information that the client needs to undertake targeted remediation, so they can fix the problems in the right places instead of blindly and hoping for the best. Okay, so with that, I think we have a few minutes left. I want to get you to a new pull in. Okay, so I wanted to show you one more case study. The next project I want to show you is a recent project we did at a copper mine in South America. So just to orient you, there is a tailings pond up here. You see the seawater pipeline here. It feeds the storage pond, and then there's also a freshwater storage pond as well. And then we've called out well CB9 here, and you know, the reason for this investigation was that the water level in the well had increased about 30 meters over a 3-month period, and it was holding steady. And you know, that was especially surprising in this area of the world because it's extremely dry and it's an arid desert. So it couldn't be really attributed to groundwater or meteoric water. And the client was getting pressure from regulators. You know, they really understood there was some issue happening with the leakage at their site, and so they assumed, based on the proximity to these storage ponds, that water was leaking out of here. And so the regulators were on them to come up with a solution to understand the problem. And so they put together a remediation plan that was going to cost them about $6 million to reline and fix these storage ponds. And we came to them and said, you know, before you do that, let us come out and do an investigation. We just want to confirm, you know, this is really the issue before you spend all that money. And so with that, we designed a survey you're seeing here with the upgradient electrode in the tailings pond, and then the other electrode we put in the well itself, and with our survey area surrounding the well, so we could get a really good understanding of what was happening. And what we found really surprised the client. In fact, it really surprised us as well. We found there was no evidence of preferential seepage coming from either of those storage ponds. But we did find that there was a preferential flow path from the northwest along these faults. And so these faults were carrying seepage from the tailings pond into the well. So I'm hoping with this, it shows the power of some of the information that we can provide as the client was in this case was prepared to spend millions of dollars fixing a problem that they really didn't have. We were able to help them understand where to focus their remediation and get the regulators off their back and really help them fix the problem. So I think with that, with those 2 case studies, that brings us to the end of this presentation portion. Hopefully these case studies help demonstrate how the technology works and some of the power that we can provide to our clients. And with that, I'll turn the time back over to Alistair.
Thanks, Ryan. That was really, really interesting. And it's not hard to see that how versatile the technology can be, from even to, you know, mapping underground stream flows or leakage from canals and rivers and the like. What I'll do now is I'll welcome any questions people might have, and you should have a little hand up sign that allows you to join the question queue, or you can simply type in your question into the chat box at the bottom. And we have a question here, so from Sally. So I'll just give you the microphone, Sally, and if that doesn't work, please type your question into the chat box. Just while we're waiting for Sally there, I will point out as well that I'll send around a recording of the web, a link to the recording for everybody, as well as the links to the videos that Ryan showed as well. Sally, are you there?
Hello.
Hi, Sally. Yep, we can hear you.
Oh, hi. How you doing?
Well, thank you.
Just wondering if you've ever used this in a landfill application. Like you mentioned with a lot of the metal interference, it's good to know what you have there before. If you've got no idea what you have in your landfill, is that going to affect this detrimentally?
That's a good question, Sally. In fact, we've done several landfills, and the technology works really well in landfills. Now, you have a good point that there is conductive culture in the landfill, but we're able to filter it out as well. And Sally, if you want, after the call today, I can have Alistair send you a case study example of a recent landfill project that we did.
Yep, I'll definitely do that, Ryan. I'll just have to just turn Sally's volume off a bit because we're getting a bit of feedback, but I'll send through that case study. Thank you for that question, Sally. And Ryan, can you see there's a question from Steve in the chat box there about the potential difference of the power source?
Yeah, potential difference you use in your power source. So maybe explain just a little bit more what you mean about the potential difference using in your power source. I mentioned earlier that we do use a signature frequency, which is 380 hertz. But maybe be more specific on the question, Steve, if you could. Ah, okay, good. So the voltage. So yeah, very good question. We use very, as Jared mentioned, very non-intrusive. We use between 0.5 and 2 amps. And the voltage that we're putting in there is less than 300 volts into the ground.
Thanks for that, Ryan. And a question from Dana about I think spatial variation in groundwater salinity and how that is compensated for in the modelling.
Yeah, I think so. I think that's Dana's question. So related to groundwater salinity, I think what you're talking about is the high conductivity of salts and that. Is that right, Dana? Maybe you could just confirm that. Okay, so yes, there, and I want to make it, and I don't know if this is going to answer the question directly, but there is a difference between pore surface area dominated materials and pore volume dominated materials, and in this regard, there's a log linear correlation exists between electrical and hydraulic conductivities for poor surface area dominated materials. And for poor volume dominated, for poor surface area dominated materials, we must take care in the electrode placement and the interpretation. But we've been very successful in those areas where you have clay-rich environments to distinguish the flow paths of zones of greatest transport porosity. I help answer, Dana?
And while waiting for Dana there, John asks, I think, about whether or not Willowstick can be used to show a negative, I suppose, no flow or.
Okay. That's actually a good question, John. And it is important to note that with especially with mining projects where you're looking for mining works or whatever. The way our technology is set up and the way it works is you must have conductivity, contrast, and you must have connectivity. And so in order for ours to work, we need to have a flow path there. And so our technology, while it works, it is not very good in working with just geological structure. Meaning not having any flow paths or not having any water in those zones.
And Mark has asked a question, Ryan, about the scalability and I think about the wild seed leaking pipe application.
Yeah, okay. So yeah, how scalable is the resolution? So the best way I like to answer that is I don't think I mentioned, but when we do grid spacing on many of our projects, we're typically going to be about 5 by 5 meters or in 10 by 10 and 15 by 15 meters spacing apart from each one of our measurements. And there are other variables, but the best way I'd like to describe it is if we're doing a 5 by 5 meter grid spacing with our measurements, you typically will get to a resolution of about 2.5 meters. And then on a 10 by 10 meter, you're getting a resolution to about 5 meters. Okay. Now, in the case of leaking pipes, when we're going through a tunnel or through PVC pipe, the distance when we're going through that, we're using a little bit different technology in that we're able to detect the leakage zone within inches and within centimeters of that leakage that's going out. Hopefully that answers your question, Mark.
Excellent, right? Thank you.
John,
Sorry.
Yeah, I do see John's follow-up question or his follow-up comment. There is groundwater in each compartment that we're trying to see whether flow is continuous or disrupted by faults. I think that in this case, it would be really good to get our chief engineer to look at the exact area. If you've got some more information on those specific zones, then the power of this is we can tell you whether our technology is going to be very applicable for this or whether it will not. It only takes really a day for us or two to look at the data and then provide you with a thumbs up or thumbs down as to whether it will be applicable. And I think that your follow-up comment seems to apply to a good application for our technology. We just have to look at it a little more closely.
I think you touch on a really important point there, Ron, about going through the process in working out the feasibility of Willowstick for your project, and that it's very much a two-way, dynamic, communicative process where we have a series of questions and information that we'd like from you to be able to have a look and do a sort of a pre-proposal about the applicability of Willowstick. So we really welcome, and we welcome you to get in touch and just workshop your particular project. So it's not a technology where we expect to be, it to be just grabbed off the shelf blindly and used, but really talk with us and talk with Willowstick together to see the value in this technology for your particular project. As I said,
yeah, that's a really good point, Alistair. And I think that it's important to understand. I mean, we do not charge for any of the consulting services until really we put a proposal together. So we love to look at the information that you might have. And there have been a few projects that just have not been applicable. And we'll tell you that up front. Our reputation is so important. We've done, again, as Jared mentioned, we've done almost 275 projects worldwide, and we have a very good rate of people coming back to us and doing consequent projects with us because they've been impressed with the technology. And so we like to be able to know before we actually go out to your site that it is going to be successful. And so we'll tell you that up front.
Yeah, so I think there might be a couple of final questions or comments coming through in the chat box, but as we wind it up, I'll just remind everyone that I'll send through the link to the recording as well as a link to those videos and the contact details where you can get in touch directly to discuss your project. I'll send through the list of pre-proposal questions, which really help narrow down the thinking and the discussion about individual projects, so a bespoke solution can be presented. And I'd also like to take this moment to thank Jared and Ryan for presenting this morning, and thank you everyone for jumping online. It's been absolutely fantastic.
Oh, thank you so much for again having this opportunity to share with Willowstick, and thanks to everyone for attending. And as Alistair said, if you do have any questions or potential projects here in Victoria, across Australia, more than happy to receive questions and work with Willowstick in helping you come up with solutions. I guess both HydroTerra and Willowstick, we're technology-based companies, but we're here to provide solutions as we can.
And Ryan, maybe there's final question here from Corey as a good way to finish up.
Yeah, okay, I see that. What sort of depth resolution can be achieved, particularly if one feature underlies another? I'll explain this in that I think Jared mentioned that this is similar technology to like an MRI. But unlike an MRI, where I don't know if any of you have gone in to a doctor, they usually will take an image of your body all around the body. In our case, we're limited to just the surface, so we're not able to get all around the area of investigation. And so when we talk about depth resolution, it's a little bit different in terms of longitude and latitude coordinates that we give you. We feel very accurate in that. The best way I can describe on depth is that, let's say that we identify a flow path that's, say, 100 meters down. Then that 100 meters, we give or take about 5 to 10% in error of margin. And what that means is we typically like to, if we're identifying it at 100 meters, we're going to err on the side of going deeper. So we're talking maybe 105 to 110 meters, because if you're drilling down to confirm and ground truth, then you'll be able to hit that at least before the 110 meters. But so in depth, it gives you a little bit of a percentage of about 5 to 10%, depending on the application. There are other variables which I won't get into specifics about. That's a good question there. Thanks.
Thank you, Ryan. Really appreciate your time this morning. It's been fantastic.
Okay, well, thank you very much. I appreciate it, and I look forward to further discussion with any of you who might be interested in discussing a particular project in detail.
Fantastic. Thank you, everybody. Much appreciated.
Thanks, Ryan.